So we talked earlier about using a formula as a template to, with general parameters as a template to solve other problems that are kind of have the same form. And so we're going to look at another example of that here. So this is why I'm calling this reusing general formulas. So we'd like to be able to use standard formulas to simplify output calculations, and the same thing as a geometric series here, and then also be able to use block diagrams to simplify the convolutions that we're trying to write. So as a starting point, let's look at convolving two decaying exponentials. So we have x of n is alpha to the n u of n, and beta and h of n is beta to the n u of n. And we'll assume that alpha is smaller than beta, and that'll just be important to kind of make sure that we have the right terms at the end. Right, and so we can see that x of n this would correspond to alpha less than 0, and this is sort of beta greater than 0, but you can have any sort of, both of them can look something like this. So again, we can have some fun with summations. Let's just plug in x of k and h of k into the convolution formula. So here I'm going to take alpha to the k, beta to the n minus k, and then I get a u of k, u of n minus k. And I can use these u's now to constrain this, this summation. So we need k has to be greater than or equal to 0, and the second one says that k has to be less than or equal to n. So we're going from k equals 0 to n, and we get alpha to the k, beta to the n minus k, u of n. Now notice we're summing over k and not summing over n, so we can pull out this beta over n over here, and we'll get alpha to the k, beta to the minus k, which is the same as alpha over beta to the k. And we just have this u of n that also can get pulled out. So then we just use our geometric, so here we use geometric series, and then we do a little bit of cross multiplying and so on, and we can get this nice form in the output. So it's beta to the n plus 1 minus alpha to the n plus 1 over beta minus alpha. So this formula is very useful. This is, again, a general template that we can use. And it's very useful when we're faced with convolutions which look something like, you have a decaying exponential, and you have some delay, and maybe you have this n plus 2, which is not quite equal to n, and this is n minus 1, which is not equal to n. So the question is, how do you deal with these types of convolutions? And obviously step 0 is to draw a picture, always draw a picture. And this time you want to draw a picture of how you get these signals from signals that you know about. Like, you know how to get alpha to the n u of n, right? You know what to do with that one. But how do you get something that looks like this out of something that looks like this? And that's the question. So how do I process this signal here, to get something that looks like this signal here? So we can write it out. We can say, how did I get my x of n and h of n from the previous example? Right, so first off, I had a u of n minus 1 in the first term and u of n minus 4 in the second term, so we can create those by introducing a delay. So I take a system that has impulse response delta of n minus 1. This is a delay by 1. This is a delay by 4. So it's basically a combination of a delay and a gain. So delay plus gain will give me both x of n and h of n. And here we're looking at the alpha and the beta. Alpha is less than beta in this example. So the question is then, how do I use this block diagram representation to understand what's going on, and how do I convolve x of n and h of n in the end? What does this buy me is a real question. So to combine these, let's define sort of the template functions a of n and b of n, which are our two functions that we know how to convolve together. So we know how to do. So we know a star b, and that is, we have a formula for that. And so now we can write x of n as b convolved with a delay of 1 and a gain. The gain is going to fix up this exponent over here, right? And h is a convolved with a delay convolved with a gain. So since we want to find x star h, it's going to be all this stuff star all this stuff. And then since convolution is commutative, we can gather terms. So we're trying to gather terms. And which terms are we trying to gather? We're trying to gather this. We get this n minus 5, and that comes from the n minus 1, the n minus 4. So this is 4 plus 1. So this is a total delay of 4 plus 1, which is equal to 5. So we have this 5 here. And they have 1 over 2 to the 3 times 1 over 5 to the 3. So that gives me a 1 over 10 to the 3. So this is a total. We can call this the total gain. 1 over 2 times 5 to the 3. And then we just apply these delay and gain to, finally we have this this template. Sorry, this U event should also be included. We have this is from the template. Gathering like terms, we get something like 1 over 300, 1/2 to the n minus 4. And then we can get, again, a minus 1 over 300, 1/5 to the n minus 4 u of n minus 5. And that's just gathering the like terms together. So I think the main point is that this example, what this example shows, is the power of reusing old these kind of known templates. So that kind of using a known template, and then applying block diagrams, because I think that's the real trick here. So what's the general recipe? Suppose you know what a star b and so you know the convolution of a and b for some a and some b. If you can write your h and your x in terms of a and b, pass through some LTI filters, so that is x is, for example, a version of a which is put through some delays or gains or other LTI systems, and h is similarly, then the convolution of x and h is the convolution of all of these terms. So all of these filters here, all these filters, and then also you get this convolution a star b at the very end. So you write the output as a star b passed through the merged LTI filters. And that's the total gain. So this, remember, was the total gain and the total delay. All right, so as always, we should look at some examples to try yourself. So here are a bunch of examples you can try. Try to apply the template, try to apply the tricks. Some of these are a little trickier than others. They have n plus 3, for example, over here, and we have an n plus 2 over here. So you'll have, instead of having to look at delay, you'll have to look at negative delay or advancing the signal. So again, total delay is going to be the sum of the negative and positive delays, but make sure you keep track of the sign so that if things cancel, you can account for that.